Just as Ben mentioned, we're going to talk more about sound measurements today, or acoustic measurements. And to start with, why is it important? Let's ask ourselves, what is important to describe sounds or characterize sounds? So as we are pretty much aware of, sounds, animal sounds are involved in acoustic communication are usually specific to its species, right? And that enables an organism to discriminate a call that is different from its own, and consequently, that also enables us to attribute an identification to different species. So we can identify different species based on their sounds. And because of this central role in reproduction and sexual selection, the sounds of species are also used to describe species, like in a taxonomic level. So it's used as a diagnostic morphological attributes to differentiate different species. For instance, with frogs, that is super common. You may have two different species that are morphologically similar, pretty much similar with color, their morphological structure, but the genetics and the sounds, they differ, and that make them into categorized in two different species or two different taxonomic units. But also, just like any other sort of ecological trait or other characteristics of species, like color, size, body size, beak size, sounds are also subject to selective pressures. So we can investigate the variation of sounds in nature. By investigating that, we can better understand how really evolution is working. So for instance, we can generate hypotheses and predictions of how animal sounds can be influenced by anthropogenic pressures. For instance, we have seen this examples in the literature showing that birds and frogs whose populations are close to airports or roads with intense traffic, meaning subject to intense traffic noise from airplanes and cars, their activity levels through the day or the seasonal levels of activity or even characteristics of the sounds start to shift to avoid interference with these other pressures. Or you even can see, for instance, how species with very similar ecology and very similar sounds end up diverging in time, just like in any other sort of morphological characteristics, as it happens with character displacement, but it will be kind of a sound character displacement. And other than that, other questions, for instance, how climatic conditions affect calling activity and how a warming world will affect the acoustic behavior of species, how some populations are losing the diversity of their sounds or their repertoire because individuals are being, the populations are decreasing, and with that promoted, for instance, by disease or habitat loss, and with that we're losing the diversity of sounds as well. And how we can see geographical variations of sound. What are the factors that are related with these potential sources of geographical variation? So there are many good reasons for us to get familiar with describing and differentiating animal sounds. And the good news is that most of the measurements that can be used to describe these sounds are contained in Raven. So before we move into spectrograms and waveforms, I'm going to bring here an example of another way to visually represent the sounds. And it's going to be with this following sentence. Hello, my name is Larissa, and my dog's name is Bento. This is the one visualization of this sentence, right? And after seeing this, like the sentence and the words, how could we start describing it? So one way that we could perhaps start describing this sound that is expressed here in this sentence is by showing that, well, this sentence, the entire sentence has three clauses, these different units that are separated by a short period of time, a short pause. Or we could say that the sentence has 11 words. These different words are also separated by shorter distances between them. Okay, now here's the sentence again, now visually represented through a spectrogram. And here are the different clauses. Hello, my name is Larissa, and my dog's name is Bento. As you can see, the pauses are there, showing this differentiation between clauses, and the 11 words are also there. And if we were to do annotations on these different units that here we are calling words, on Raven, we would probably generate a column named tag and indicate what is it their categories are, their tags. So we could say this way of describing the sound components is a way to describe the composition of sounds, and this is just a way for us to go in the same terminology. And with this, well, we can also see that from these 11 words, we have 8 unique words. This one here is my, and it's repeated once again here. It's kind of this in the form of a hat, a Harry Potter type of hat. The other word that repeats is name. As you can see, there's these 2 strips of frequency that are continuous, should probably be this nasal word. And after we include the A here, we have this other sort of component that has more harmonics. Harmonics mean these different strips that are repeated at specific frequencies, intervals. And is also, is the shorter one here with this energy concentrated in this 2, from the bottom to the top, the energy is mostly concentrated in these 2 strips of frequency here below. So, well, okay, why does it matter to know these things about describing the composition of sounds? Well, it matters because for birds, primates, frogs, insects, the way that we describe sounds usually follows this sort of hierarchical organization that usually has smaller units that are then gathered into greater subunits. For instance, in this example here for birds, this author used this terminology, syllable, to indicate the smaller units. And you have different syllables, right? A, B, C, D. And a set of these different syllables together are called phrases. And they are also separated by a short pause. And when these phrases contain similar syllables, they can be considered similar phrases, just like hello, 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 being repeated. And while this other author here, the minor subunits, let's put on this way, they consider the terminology employed, it's like note, and they mention so that this species has 5 different note types, and the entire sequence of notes over time is considered a song. So, and for frogs, it's pretty similar. The smaller unit usually is called note. Some old literature also call them as a pulse, but and the set of different sequential notes together is considered a call, or and calls can have different functions, and then the calls are named after these different functions. But the terminology used also differs between groups, right? So in order for us to understand what is the minor units I'm referring to when I'm talking about frogs or birds, we have to be consistent. So it's important to search for references that describe these different terminologies and adopt a given scheme that is similar when you want to describe your sounds. And here are some examples that are also contained in our Canvas portal, showing how some of the terminologies are considered for birds. And this one here is a material gathered by this author, And the interesting thing is that the reference uses this old version of the Raven user's guide. And here are other two examples that are used to describe primate bioacoustics and frogs, neurons bioacoustics. And this one here is really interesting to be read, not only for the frog people, but for everyone that is interested in describing sounds with better settings and good practices. Okay, so another way to describe sounds, it's to describe how it is distributed over time, right? So the most common way of describing it is to say how long does it last, the duration, or delta time. And here, just to show how to enable this measurement in Raven, you will right-click your selection table, and from this menu, you select choose measurements, and then you select delta time, in here 3.1. Can you see my cursor in here? From 2.1, yeah. You select the left arrows, and then you should ensure that delta time is then displayed in the left box of this window, and then you finally select OK. This is also the same scheme for many other measurements or any measurements that are contained in Raven. So with this delta time or duration, we can take this measure for really any unit that you consider in Raven. First of all, you can select your entire sound and know what is the total time of your recording. And when I recorded my sentence, it took me 12 seconds. But the sentence that I emitted, hello, my name is Larissa and my dog's name is Bento, took only 8 seconds. So that's the delta time of my song or my call. But I could also go and measure the clauses that I've mentioned before. I have 3 clauses, and this clauses varies in time. And I could show the mean value of that. Or I could even show the mean value of the duration of the words that I'm saying in this sentence. So another interesting thing that is you can combine the composition with the duration and extract measures that represent a rate or a proportion. For instance, how many sound units you have per unit of time. And in this example, well, I had recording with 12 seconds and I emitted 3 different clauses, and that would give me an average of 0.25 clauses per second. Or in another way, I had this recording of 12 seconds and I emitted 11 words, and that will give me a rate of 0.91 words emitted per second. And just to show an interesting comparison, the average rate of words per second for the human speech is 2 words per second. So that shows that I was speaking really slow to make a beautiful spectrogram for this presentation. So here we just another way to visualize it. We can describe the duration or the delta time. Delta is simply the difference between 2 points, and here is the difference between the begin time and the end time, right? But we can also describe sounds in other axes other than time, and those are frequency and intensity, right? And the simplest way to put that, these 2 different points in frequency would be what is the lowest frequency and the highest frequency. And the difference between those would also be a delta frequency, or also called bandwidth. And as we've seen before, there is this other dimension to describe sounds, that is the intensity of sound. And that's really how we perceive sound as being louder or softer. And in Raven, we can represent that with a color gradient here shown by warmer colors to colder colors, but you can also use grayscale with darker levels of gray showing louder sounds and brighter showing softer sounds. And what that really represents is that a loud sound has a amplitude that are taller, the waves are taller, so contain more energy, and soft sounds has low amplitude waves being perceived as softer. So if you wanted to describe how the intensity of sound is distributed in this call, we could start by saying, where is the point that we have the highest quantity of energy? And this would be somewhere in here, right? Between 2 to 3.5 kilohertz. So this frequency that contains the highest concentration of energy in a selection is called peak frequency or dominant frequency, depending on the terminology used. And I believe this is one of the most important spectral measurements to describe animal sounds, particularly because it has been shown that when individuals are exposed to a range of different frequencies, the hearing sensibility is usually has more positive responses to the to the dominant or peak frequencies of its own species, of the call of its own species. It's like a mechanism of matching that is very adjusted. So the peak frequency or dominant frequency is really important to describe animal sounds. So there is a short downside of using these selections of these measurements that are based on the way that we do selections, the maximum, the minimum, and the delta. And that happens because we, as normal human beings, can do different ways to select. We can use different strategies to make selections in our recordings, right? For instance, in this one, a given person can say, well, I want to start selecting from where the sound starts to appear in the recording with that given setting in the spectrogram, with that level of brightness and contrast. And I'm gonna end the selection when I see the end of that. And that's the same for the time and the frequency. So delta time would be something like all of this, and delta frequency would be something like all of this. And then another person thinks, no, I'm going to select only the portion that I think that we have the highest concentration of energy. So look at the differences of delta time between observer 1 and 2, and the delta frequency between observer 1 and 2. And that can happen between observers and even within observers if you use different settings on the way that you visualize your sounds. So there is a way to kind of overcome this sort of variability. And this would be with the use of some measurements that are less sensitive to these differences in the way that you do this sort of selections. And these are called the robust measurements. And the robust measurements, they are taken basically on a distribution of energy over the frequencies. So here, just to show what is meant with this, we have this spectrogram. This is time, and in the vertical axis is the frequency dimension. And we're going to now convert this and put the frequency dimension as the horizontal one, but we're going to adjust it to reflect from 0 to 5. And for each of different, let's say, bands of frequency from 5 to 4, 4 to 3, 3 to 2, we're going to check the level of the distribution of the energy in these different frequency ranges, right? So, and we're going to reflect this in a graph where we translate the amount of energy that is within these different frequency ranges. So let's start with this frequency between 5 and for this band, we can see that there's only few energy, a small quantity of energy in this range. So the energy here would be reflected as with a small value. And between 4 and 3, we can see there's more energy concentrated. So our bar would be a little bit taller. Between 3 and 2, we lack some energy in here that was contained here. So our bar is a little bit shorter. Now from 2 to 1, there's way more energy concentrated. And here we can start to see some areas with darker shades of gray. So yeah, there's a lot of energy concentrated in here. And between 0 and 1, I'm going to separate in frequency ranges of 0.5. So between 1 and 0.5, there's the largest concentration of energy. As you can see, the darkest shades are concentrated in this region. So it should be reflected as the taller column in this graph. And we do also have a lot of energy concentrated here in this last part of our spectrogram, but that's consistently lower than the previous frequency range between 0.5 and 1. So this is more or less how the energy would be distributed over this range of frequencies between 0 and 5 for this selection here. So we could also see this in different manners. For instance, if I was to say, where's the 50%, where's half of the energy concentrated in this graph bar here, in this bar plot? Well, it's around here, and this would reflect to be around here. So 50% of the energy is concentrated in this region, and the other 50 over the other frequency ranges. And we could do this the same with 25%. So 25% of the energy here, and so on. And this would be reflected the same in here. It happens that with this different 25, 25, 25%, we can also call this different, after achieving the first 25%, we call this quartiles. So we have 3 quartiles, and this is a way that you can assess easily where are the frequencies that divide, that contain most of the energy contained in the first quartile, or the second quartile, or the frequency that concentrates the energy of the third quartile. So just as we've seen in the 50% of concentration of energy, for instance, here we have, let's say 100% of the energy is concentrated here, but the 50% is probably distributed in this frequency range, and the other 50% is distributed in this frequency range. So the frequency that divides this in 2 is considered the center frequency. And the same is true with the time that divides the distribution of energy of the selection in 50% and 50%. So when we're talking about these different quantities or percentages that can be used to describe the way that energy are distributed, we could use really any sort of percentage. But to start with, let's see, we can see that, for instance, we have the moment in time that we have 5% of the energy concentrated, and the moment of time that we have 95% of energy concentrated. And the difference between these two is what is called 90% duration. And the same is true when we consider the frequencies. The frequency that contains 5% and 9%, and the difference between those is considered the 90% bandwidth. So this would be kind of the core of where the frequencies or the energy is concentrated in frequency and in time. And other than that, we can also take a measure of reflecting the amount of energy in our selections. And one of the measures that is used that contains in Raven is the in-band power that is measured in decibel full scale. Sorry, FS means full scale. And it's basically a way to take the distribution of energies, but using really a density distribution of these energies and taking the average of the distribution of these energies in here. So it's a measure basically that reflects the mean value of energy in that selection. And it's going to be usually negative in this scale because the maximum value would be 0. So everything is normalized so that the 0 is the maximum peak level that is registered in this recording. Well, so far we've seen that we can describe sounds according to the composition or the different components that we have, and that can give us a sense of the repertoire or the diversity of sounds. We can describe sounds according to the composition over time, and that can be a measure of rate, and you could use call rate or note rate or pulse rate. So it's really the subunit of time that you wish to describe per unit of time. You can describe your selections based on the minimum, maximum value, and the difference between those over time and over frequency. But we know that this way of doing these measurements will be dependent on the way that you do your selections, and that's highly variable. So to overcome that, you can resort to use the robust measurements. And the robust measurements are based on the distribution of energy through time and frequency. And for that, we have just to remember that we can split the concentration of energy in different percentages where they are concentrated over time and frequency. And that can be used the quartiles or the percentage of, and the percentage could be the bandwidth or the percentage time. And we also have the center values would be the center frequency and the center time, where the energy is split in 50%. We've seen the peak or the dominant frequency. This one is super important, and it's important. It's like really not a matter of discussion for at least for birds and frogs. And we've also seen that a way to describe the energy contained in selections can be with this measurement called in-band power. It's sort of an average of energy contained in a given selection. But here's just a reminder that in some previous sessions, we saw that some spectrogram settings, specifically the window size, the way that you adjust it will change the way that you're going to visualize the spectrogram, right? So if you decrease the window size, you will see these vertical bars. And if you increase, you will see these horizontal bars. So just to remind you all, when the window size is small and you have these vertical bars, you will have coarse representation of the frequency. And when the window size is has greater values, you will have a very high resolution on the way that you're seeing frequencies. And the other way is true with time. You will have a small resolution, a high resolution of time, and a low resolution of time with higher values of window size. And why does it matter? It matters because the way that you will set your window size will influence the resolution of the frequencies and time that you're taking the measurements. And because of that, the values will likely change as well. I've made one exercise with a frog calls, and according to the different size of the windows, 256, 512, or 1024, the dominant frequency or peak frequency changed between 200 hertz or 300 hertz, 400 hertz, and so on. So specifically, these measurements will probably be influenced by the window size that you're using. So when you're describing sounds, it is also interesting to report the window size that you're using in your analysis, so that if you can probably replicate that and see if the matter is the window size or if the sounds like that as well. And how to set the best window size, that's a little bit with it depends on their sound. If your sounds are composed of notes that are short in time and consistently repeated, you will want a resolution that is fine in time and can represent it. So if you hear something that is trilled, but in your spectrogram that is all blurred, you will know that something is wrong in there. So you might need to decrease your window size. So this is with describing sounds. And before we go to the exercise, we can open the discussion, open the stage and see if someone has questions about it, about any of the measurements that we've described here before. Thank you, everyone, for your attention.
Just